So your reactor becomes a lot smaller when it's a reversible reaction, but you also pretty much cut your conversion in half. And then just repeats the same thing for a CSTR. So pretty simple. This is your same rate equation that you use for the CSTR. Again, just use a different design equation.
How did you get that new rate equation?
How did you get what?
The new rate equation.
So to get the new rate equation, you use you recognize that it's at equilibrium, right? So you can, so your new rate equation is going to be, you have to take into account the equilibrium constant. I think I actually wrote this on, so it'd be called. So your unit rate equation is going to be, in terms of concentrations, is your K forward times CA minus your products over the equilibrium constant. And this is just going back to, like, I think it was the very first or second lecture where I covered equilibrium kinetics. And you have to include this equilibrium term, which basically just accounts for the rate of products going back to reactants.
Why did you say that RE was equal to 0?
Because at equilibrium, you know that your forward reaction is equal to your reverse reaction. So your net consumption or formation of product A or reactant A is going to be 0 because it's being generated at the same rate that's being consumed. So it's going to be, I mean, it's at equilibrium. And then this Kc term over in this equation is Kf over Kr. So this is basically just accounting for the reverse reaction. And that's where that rate equation comes from once you plug in the mole species balances from the stoichiometry.
Question.
Yeah.
I've been trying to find a book because there's a formula that was in the book that I used to solve an homework problem that is used for equilibrium, and it looks similar to that. And I was going to ask about it, but I don't remember the equation off the top of my head. It was negative RA equals CA naught times in brackets 1 minus X minus like epsilon over X or something like that.
Was it X over KQ?
Yeah, or yeah, something like that. And I was gonna, I don't remember the formula off the top of my head, and I was gonna ask about it, but I don't have a book, so.
Yeah, only about the old edition, so I'm not sure where it'll be. Yeah, feel free to drop by in office hours or see homie. Look into it. So the final part kind of throws a minor twist into this whole problem, where they basically said that your reactor is now a membrane reactor, and you have dissipation of the ethane out the sides of the reactor. So, is everyone good if I erase this? So your PFR becomes a membrane reactor. Then you have mass transfer out of the sides, but only B can pass through the membrane. And it gives you a transport coefficient for B of coefficient of 0.08 inverse seconds. And so really all this changes is you also have to account in the mole balances of mass transfer out of the reactor of B. So do you guys know how you do that? Is everyone pretty comfortable? You've all taken mass transfer? Okay. And so they basically tell you have this membrane reactor and redo all the sizing steps. Or at least for a PFR. So you get it's also still at equilibrium, by the way, this part of the problem. So your rate equation becomes I'm on the wrong page. Bad. So for this problem, it's actually easiest to approach it in terms of flows and not concentration. So you would do a flow balance. And then you know that you basically have to do a rate equation for each species in terms of, well, rate of change of flows. So for A, you're just going to have a B or positive RA, since they define RA as negative K. And then for species B, it's going to be negative RA, since RA is the generation of A. It's going to be negative RA, so the formation of the product, minus the mass transfer coefficient times the concentration times the part of the flow that accounts for B. And so this is the only real change in how you'd approach the problem with B leaving out the sides. You just have to include this mass transfer term.
What's RA negative?
So actually, so this is the rate of consumption. So this is no. So they define RA as negative K. So it's rate generation of A. So it's the rate of consumption of B minus the mass transfer out of the reactor. So it's just heuristics how you define.
B equal to just RA?
Huh?
Since they define the RA as negative.
So no, it'd be, so if RA is this rate of generation of A. Yes, this is rate of. So this is basically accounting for the rate of product going to reactant, so that's why it's negative.
Right, right. But then in your first.
No, so this would still be positive.
Right. Is that a negative sign there, or is that just bad erasing?
No, this is bad erasing, sorry. Yeah, good call. And then you just have twice the formation of C as A because of the stoichiometry. Then you can also define your rate equation in terms of flow. It's going to look pretty similar to concentrations. then, apart from this, so if you wanted to make a plot of the relative rates of formation or dissipation of species, you can plug it into, for instance, they use polymath, and you just put your conversion as a function of A over the total flow rate, which is 2.5. So you start off complete A, and then do diminishing A. And then if you wanted to plot this, your plot would look. So this is very good. So for A, you'd start off with complete A, slowly diminish over time. For B, you'd have a slight increase and then a decrease as it starts to exit out and become free or return to reactant. And then C, it's just monotonically increasing